Welcome back to our videos. Today we're going to introduce the first algorithm to minimize a function. And we're introducing that for minimization, but of course it can be easily adapted to maximization as well. And that algorithm is gradient descent. Remember, in one of the last videos, we've talked about the interpretation of the gradient, and we have seen that the negative gradient is the direction of steepest local descent. So that's the direction we want to follow if you want to minimize the function value. And that's exactly what this gradient descent algorithm does. It follows that direction of local steepest descent. It does that for a while, and then it just reevaluates the gradient, changes the direction if necessary, and does that as long as necessary. So let's write down how this algorithm works. That's our first algorithm. For minimization, that is gradient descent. And let me just add a quick note here. So we present that for minimization. Of course, it can easily be adapted to maximization. Okay, we will present the minimization version. But the algorithm can easily be adapted for maximization. Okay, how does it work? Let's first see what input the algorithm gets. The input is a function that is continuously differentiable, and we'll say it's continuously differentiable on Rn. Of course, we could also choose a domain that is contained in Rn somehow. We just have to make sure that the algorithm never chooses a point outside of that domain. So to avoid these technicalities, we just work on Rn for now. And we need some initial value. So some point, we'll call that x0, that is contained in Rn. Doesn't really matter which we choose. And the output that we expect is some point x star in R to the n that approximates a local minimizer. At least that's what we want out of the algorithm. And how does it proceed? Well, it starts with a quick setup. We just set a counter. We call that k. The counter will start at 0. And then we'll initiate a loop. And we'll repeat some steps until we are satisfied. And we will be satisfied once we reach a point where either the gradient is 0 or at least below a certain threshold value. So we will repeat those steps if the gradient is not 0, or if we want a looser approximation, if the norm of that gradient is above that threshold still. Okay, so while the gradient of our current iterate, that will be called xk. So in the first round, that's the initial point x0. While this gradient is not 0, we'll do the following. Or we can also impose the condition that the norm of the gradient is above a certain threshold value epsilon. So while that's the case, we'll do this. We'll first set a direction. And that direction is going to be the negative gradient. So minus f of xk. So we evaluate the gradient at the current point, xk. We take the negative gradient, that's the direction of steepest local descent. We don't care about the length of that gradient for now, because we're going to scale it by some step size anyway. So the length doesn't really matter. So next thing that we do is we find a lambda that is positive, such that if we move away from xk in direction v for a step size of lambda, so we scale that direction with lambda, we move away from xk in that direction, and how far we move, that will be determined by lambda. And we say we move far enough or not too far so that the function value actually decreases. Right? We know we found the direction of steepest local descent, so as long as we're close enough to xk, there will be some decrease. But maybe if we move too far, of course, then our approximation is not good anymore, and that means then we may hit an ascent or a point where nothing changes. So we just have to make sure that we don't move too far, and that's what this lambda does. Okay, and once we found that step size, this lambda, then we actually do the move. So next thing we do is we set xk plus 1, the next point in our iteration, to be xk plus lambda v. So we move away from xk in negative gradient direction by that step size that we determined. And then we just increase k by 1. So set k equal to k plus 1 and repeat the loop. So that's where this loop ends here. And once we're done, we have a point where the gradient is 0, and we've decreased function value, so that should be a local minimum. And that means we just return that point, x star, that is simply the current iteration xk. Okay, so let me just make a quick note of what I told you already. This lambda here, that is called the step size of our move. And of course, one thing that I didn't specify yet is how will we actually find such a lambda? And that's a non-trivial question. How do you make sure that you do not move too far, too fast, so that you actually get a function value that is better than the one that you started with? And basically, I'll present two methods for doing that. So that's the point that is missing from our algorithmic description. That is, how do we choose that lambda value? Choosing the step size lambda. I'll just sketch two quick methods to do that. The first one is called a line search. So what you could do is you could regard the function lambda maps to the function value of xk plus lambda v. You could regard that as a function of lambda. So that's a one-dimensional function, and we know how to minimize one-dimensional functions, so let's just do that. Find the best possible lambda, and that's the minimum of that function. Okay? So what we do is determine lambda as minimizer of this function here. That's probably the best that you can do, but of course it involves some degree of computation. You have to actually determine that minimum, and that is some work that's involved here, especially if f is costly to evaluate. So in some cases, a quick heuristic might actually be the better choice. And that heuristic just proceeds as follows. It starts with a certain lambda value. Let's just say we set lambda to 1 in the beginning. And then we just see if it works. So if f of xk in any iteration plus lambda v, if that is too large, so if it doesn't give us a decrease, then that means we have to try a lower level of lambda. So we set lambda to 1/2 of lambda. We just divide the value of lambda by 2. And we repeat this procedure as necessary. And repeat until we actually get a decrease. So until this condition is satisfied. And we just keep that level of lambda. Of course, while this will work, it will probably lead to very, very low levels of lambda very quickly. So we'll also incorporate a means of increasing lambda if we can afford it. So if f of xk plus lambda v is less than f of xk, then try to double the value of lambda and use this new value if there is still a decrease in function values. So that is to make sure that we don't get a very, very, very low, small lambda, and then just keep at that and hardly make any progress. So that's to ensure we make sufficient progress if we can. Okay, so that's the idea of that simple heuristic. We just adapt the step size to the current situation. And of course, there are many, many more ways to choose lambda. That's an art for itself, but we will not go deeper into that topic here. Okay, we'll see an example of that in one of the coming videos. And then, of course, we'll also see one other method that is a little more sophisticated than simple gradient descent. But that's it for today. Thank you.